Dear students, again welcome back for the last session of this particular physical topic that is called as solutions. Previously we have discussed the four different colligative properties that is called as lowering of vapor pressure, elevation of boiling point, depression of freezing point, and then just I mentioned only the definition with respect to the osmotic pressure. Okay, so now we have to prove that osmotic pressure is an example for a colligative property. So that can be done with the help of one theory. That theory is called as Van 't Hoff's theory of solution, dilute solution. So before that, what is osmosis and what is osmotic pressure and what is reverse osmosis? Let's have the brief definition for that. So what is that first osmosis here? We can have the two definitions, but both will have the similar meaning or the same meaning here. The first one is the process of movement that is also called as a flow of the solvent molecules from the region of its higher concentration to the lower concentration through the what membrane? Semi-permeable membrane. That is one definition. Another thing is this process of movement or flow of the solvent molecules from the region of or from the solution of lower concentration to the higher concentration. Both have the same. In the first definition I mentioned only high to low, but we have not used the term called as solution. But in the second definition it is from lower concentration to which one? Higher concentration. Here I have used the word called as solution. Indirectly both will have the same meaning because the lower concentration of a solution means higher concentration of solvent. Higher concentration of solution means lower concentration of which one? Solvent. Okay. If this be the case, the solution of lower concentration to higher concentration or from the region of its higher concentration to lower concentration through the semi-permeable membrane refers to what? Osmosis. Then what is that osmotic pressure here? If I apply the pressure, because as if you know that the spontaneous process is your osmosis, because it is a flow of solvent molecules spontaneously from high to the lower concentration. But the thing is, if I apply an external pressure called as an hydrostatic pressure on the solution side, for example, the flow of solvent molecules doesn't occur. Means there is no flow of which molecules? Solvent molecules. No movement of solvent molecules means we can't have the phenomenon called as which one? Osmosis. And what the external pressure that we have added to prevent this particular osmosis is called as what pressure? Osmotic pressure. Okay. So then what is reverse osmosis? Suppose it is also the same thing. It is also the flow of solvent molecules from the region of its lower concentration to higher concentration. Means the solvent will move from the lower concentration to higher concentration. It is not possible spontaneously. By applying the pressure which is greater than the what pressure? Osmotic pressure, that refers to what? Reverse osmosis. Means the reverse osmosis can take place if the pressure what we have applied is going to be greater than the what pressure that is required. The osmotic pressure that has been required is called as what pressure? What osmosis? Reverse osmosis. So that is the very best example that we have already mentioned for the purification of water, or indirectly it is called as a desalination of water. Means the removal of the solute or the salt particles from the sea water for the purification of that particular water. That is called as a desalination of which one? Water. Okay. So now to prove that it is an example for a what? Colligative property, we need one concept that is called as Van 't Hoff's theory of which solution? Dilute solution. So here we are having one statement that is that at constant temperature the osmotic pressure of a dilute solution, again it is restricted only for the dilute solution. Okay. The osmotic pressure of a dilute solution is equal to the pressure exerted by the which particles? Solute particles. If it was considered to be a gas. Means we are assuming or we are considering that particular dilute solution is behaving almost as that of a gas and also occupies the same volume as that of particular what solution? Dilute solution. So this is the statement first. Then how to explain that particular concept? That is, let us take the two containers. Okay. Let's suppose that this is considered to be the gas now. According to kinetic molecular theory of gases, according to what? Kinetic molecular theory of gases, what a gas consists of? It consists of a very small, which is also called as a tiny, and then the discrete particles called as gaseous molecules. What molecules they are? They are the what molecules? GMs. GMs means it is called as gaseous molecules. Okay? Now, what these gaseous molecules are doing, they are freely moving in the space or in the container here right now. Suppose if one gaseous molecule collide with another gaseous molecule, it is a property of elasticity such that they change their what direction, because they always move in a straight line. If the collision takes place between the two gaseous molecules, yes, there is a change in direction to prove the property called as elasticity. Suppose if this particular gaseous molecule is colliding against the walls of the container, it creates a pressure, and that pressure is called as pressure exerted by the gas. Means how the gas exerts pressure here? Due to the what? Collision of the gaseous molecule against the walls of the container. It is not again between the two gaseous molecules. The gas can exert the pressure if and only if the gaseous molecule collides against the what? Walls of the container. Means the pressure of the gas inside that particular container is due to the collision of those gaseous molecules against the walls of the container. Now this is in concentration with another that is called as dilute solution. Let us take, this is first a dilute solution. What's a dilute solution? A solution of lower concentration. Solution of what concentration? Lower concentration. What's the meaning of lower concentration here? A small amount of a solute is dissolved or added to the large excess of which one? Solvent. Means, as if it is a dilute solution, means we are having a very small number of which particles? Solute particles. What these are? These are called as which particles? Solute particles. Why I am writing the very simple or very small number of solute particles? Because the solution that I have mentioned is going to be the dilute. Okay? Again, what those solute particles are doing here? Again, they are freely moving. Yeah? Freely moving. As if they are freely moving means one solute particles may collide with the another such that there is a same collision between them, just they change their what? Direction. Suppose if the same solute particles which is about to hit or collide against the walls of the container, it also creates a pressure, and that pressure is called as pi. What is pi here? Osmotic pressure of which solution here? Dilute solution. This is the pressure exerted by the gas. How the pressure exerted by the gas? It is due to the what? Constant collisions of the gaseous molecules against the walls of the container. Then what is that osmotic pressure of a dilute solution? It is also the constant collisions of the small number of which particles? Solute particles against the same walls of the which one? Container. And that creates a pressure, and that pressure is called as what? The osmotic pressure. Now we are familiar now. Here gas is equivalent to liquid. That liquid is preferably the what solution? Means we are equalizing, we are comparing. Which is equivalent to which here? The gas is in compare with respect to only the solution, even though it is a mixture, but it is a dilute solution here. Because gas consists of gaseous molecules, dilute solution consists of small amount of which particles? Solute particles. Gas consists of small number of which molecules? Gaseous molecules. Similarly, they are equivalent to small amount of which particles? Solute particles. Which particles they are? The solute particles. What the gaseous molecules will do? They will collide against the walls of the container, and that create a pressure, and that is called as pressure exerted by the gas. Pressure exerted by the gas. Again, this is equivalent to what the solute particles in the dilute solution is doing. Again, they are constantly collision against the walls of the container, and this pressure is called as pi of ds. Means osmotic pressure of the what solution? Dilute solution. I think based on this now we will have the clarity with respect to this statement. What is the statement here? At what temperature? Temperature means the constant. The osmotic pressure of the which solution? Dilute solution. The osmotic pressure with respect to what solution? Dilute solution is the pressure exerted by the which particles? Solute particles. It's the pressure exerted by the what particles? Solute particles. When? If and only if it was considered to be the gas, means the dilute solution is remembering or it is resembling as that of which one? The dilute solution is in comparison or the resemblance with respect to which one? The gas. And also it occupies the what volume? Same volume as that of what solution? Dilute solution. The statement itself very clearly says that here we are equalizing or comparing. The gas is always equivalent to what solution only? Dilute solution. The gas consists of a gaseous molecule, whereas the dilute solution consists of a small amount of which particles? Solute particles. The gaseous molecules collide against the walls of the container to create a pressure, and that is called as pressure exerted by the gas. Similarly, the smaller number of the solute particles present in the dilute solution is colliding against the walls of the container, and that pressure is called as the osmotic pressure with respect to what solution? Dilute solution. So based on this comparison, Van 't Hoff has stated one statement that is called as Van 't Hoff theory with respect to what solution? Dilute solution. What is that? At constant temperature, the osmotic pressure of the dilute solution is always equal to what? The pressure exerted by the which particles? Solute particles, if it was considered to be a gas and occupies the same volume as that of what solution? Dilute solution. So this is called as the Van 't Hoff theory of dilute solution statement. Okay. Now, as we have mentioned, the liquid is in comparison with the gas here, or the gas is in comparison with the liquid. So here, that liquid is strictly not an individual liquid, it is always a mixture. Okay. So as gas can have the satisfy the various gas laws, means here also we are having some laws here that is called as. So after, let us remove this one. I think Van 't Hoff's laws of osmotic pressure. Van 't Hoff's laws. Van 't Hoff's laws of osmotic pressure. As the gas can satisfy the various which one? Ideal gas, if it is satisfy the what laws here? Gas laws, means here also the some of the dilute solution will satisfy some laws, and that laws are called as Van 't Hoff's laws of what pressure? Osmotic pressure. So let us have the first one. Van 't Hoff's Boyle's law. Van 't Hoff's what's law here? Boyle's law. So here, as if we know that Boyle's law, I think P proportional to 1 by V if temperature is constant. The pressure is inversely proportional to its volume if the temperature remains the constant. Similarly, I can have the same thing here. Pi inversely proportional to its volume. Pi inversely proportional to its what? Volume. If T is constant. Therefore, how to state that? At constant temperature, the osmotic pressure of only the what solution? Because it is Van 't Hoff theory is applicable for only the what solution? Dilute solution. Therefore, at constant temperature, the osmotic pressure of the dilute solution is inversely proportional to its volume. Okay, so that is the statement here. Let's have the second one. Van 't Hoff's Charles law. Let's have the second one in the form of Van 't Hoff Charles law. What the Charles law has mentioned? Usually, V proportional to T if P is kept constant. Or indirectly, we are having one law that is called as Van 't Hoff Charles law. Only the Charles pressure law. Or sometimes it is also called as Charles pressure law, which is also called as the Gay-Lussac's law. P proportional to T if V is kept constant. Means the pressure exerted by the gas is directly proportional to what temperature? Absolute temperature if the volume of that particular gas is found to be constant. Based on the same, we are having another law that is called as Van 't Hoff which law? Charles law. Pi proportional to T if C is constant. At constant concentration, instead of volume, we have what you have mentioned here. It is the concentration is kept constant. The osmotic pressure of only the what solution that you have mentioned here? Only the dilute solution varies directly to its what temperature? Absolute temperature. Okay. Let's have the third one. Van 't Hoff Avogadro's hypothesis or Avogadro's law here. The same thing. What's Avogadro's hypothesis here? At constant temperature and pressure, equal volume of all gases contains if both which and which are kept constant. Instead of that, pi proportional to n if both the temperature and C kept the constant. Here we are having the, instead of temperature and volume, here the temperature and which are constant. Concentration is constant. If that be the case, the osmotic pressure of a dilute solution varies directly to the what? Number of moles of that particular solute particles present in that. What happens when I combine all those here? V proportional to 1 by P, V proportional to P, and then V proportional to N. By combining all, we mentioned V proportional to N into T divided by P. V is equal to R into NT divided by P, or PV is equal to what? RT. NRT. What's this? Ideal gas equation with respect to how many moles? N moles of a gas. So same thing here. Combining which and which and which? These equations or these laws. What I can mention? Pi proportional to N, pi proportional to T, and pi proportional to 1 by V are inversely proportional to V. Pi proportional to N according to Van 't Hoff's Avogadro's law, pi proportional to T according to Van 't Hoff Charles law, and pi inversely proportional to V according to Van 't Hoff's Boyle's law. R. Pi is equal to R into NT divided by V. R. Pi V is equal to nRT. What is this? Pi V is equal to nRT. This is called as Van 't Hoff's combined equation. What equation? Van 't Hoff's combined equation. Instead of that, here. So here, what is R here? It is there we are calling that as a gas constant, but here now we are mentioning that it is having a same, but it is having a different name that is called a solution constant, but the value is going to be very similar, because as if the gas is comparison with respect to the solution, preferably the dilute solution, that is why instead of gas constant it is mentioned as solution constant, but it is having the same value. What is that value here? 8.314 joules per Kelvin per. Okay, so this is called as what? Van 't Hoff's combined equation with the help of Van 't Hoff's laws of what pressure? Osmotic pressure. That Van 't Hoff's laws of osmotic pressure is derived from what law here? Van 't Hoff's theory of dilute solution, where the gas is always in comparison with respect to the dilute solution. Gaseous molecules are in comparison with respect to the solute particles, whereas the pressure exerted by the gas is exactly equal to the osmotic pressure with respect to what solution? Dilute solution, which is indirectly the Van 't Hoff theory of which solution? Dilute solution. Okay, so that is about the Van 't Hoff's laws of which pressures? Osmotic pressure. Okay, so now we have to prove that it is an example for a what? Osmotic pressure. Sorry, we have to prove that it is an example for a colligative property. To prove OP is a CP. OP is a what? CP means osmotic pressure is an example for a what property? Colligative property. So here, by Van 't Hoff's combined equation, what is equal to what? Pi V is equal to what? RT? nRT. Pi V is equal to what? RT? nRT. Pi is equal to N by V into RT. Pi is equal to N by V into RT. Pi is equal to C into RT. Because what is number of moles by volume? It is also called as concentration. C. Number of moles by volume is nothing but which one? Concentration. Okay. At constant temperature, can you say that RT is constant? Means if temperature is kept constant, means what is the value of RT? That is also constant. Therefore, pi is equal to constant into C. Pi proportional to C. Pi proportional to what? C. What's the meaning of that here? Osmotic pressure depends upon the concentration with respect to all these are studied under dilute solutions. Means where the concentration depends on, or how the concentration depends on, it depends upon the number of moles of the solute particles with respect to the dilute solution. That is why it is an example for a what? Colligative property. As osmotic pressure depends upon the concentration with respect to the what solution? Dilute solution. It also depends upon the number of moles of the solute particles, but not upon its either the chemical nature, or it may be the size, or sometimes it may not be depend on the solvent. It strictly depends upon the amount of which particles, solute particles. That is why it is an example for a what property? Colligative property. Okay. So that is about the proving of what? The osmotic pressure, an example for a what property? Colligative property. Means first you have to take the what equation? Van 't Hoff's combined equation. That Van 't Hoff's combined equation is given by pi v is equal to what? N into RT. Or shifting v towards the right side. Therefore pi is equal to what by what? N by v into RT. But what is N by v also called as? It is called as molar concentration, or sometimes we can mention that as a molarity also. Therefore pi is equal to N by v into RT, means it is pi is equal to C into RT. As if the temperature is kept constant. R is always a constant. Therefore, what is the product of R into T? That is also a constant. Therefore, at constant temperature means RT value is constant. Therefore, pi is equal to constant into capital C. Or if I remove the equal sign, it becomes pi proportional to C. Means the osmotic pressure of the dilute solution depends on the osmosis. Which one? Molar concentration of a solution. Molar concentration of a solution depends upon what? The number of moles of the solute particles in it, but not upon its either the chemical nature or it may be the size. That is why it is an example for a what property? Colligative property. Next we will have the expression for molar mass, or it is also called as molecular mass of a solute using osmotic pressure. Using what pressure? Osmotic pressure. With the help of osmotic pressure, we have to prove that it is an example for a what? Colligative property. So here, from Van 't Hoff's CE means Van 't Hoff's combined equation. Pi v is equal to what are the here we have mentioned? nRT. Pi v is equal to nRT. Pi v is equal to W by M into RT. W by M into what? RT. M2 is equal to, or M is equal to first, WRT divided by what? Pi into V. As if it is a solute means it is considered to be the W2, sorry M2. M2 is called as molecular mass. Means if this be the case, it is W2, means mass of the solute into solution constant called as 8.314 into absolute temperature, osmotic pressure, and V is the volume of that particular dilute solution. So this is the expression with respect to which one? The molecular mass of a which one? Solute. Okay. And another term is, another important term that you have to know is about this one. There is a direct, that is pi is equal to what? CRT. Sometimes it can also be mentioned as MRT also, where M is called as molarity. In general, it is C is called as what? Concentration. Instead of concentration, suppose if it is number of moles per dm cube, means it is called as what? Molarity. Okay. So that is about the proving of osmotic pressure as an example for a what property? Colligative property, and also the expression for the molecular mass. Molecular mass is given by M2 is equal to W2 RT divided by pi into V. What is M2? Molecular mass of the solute. W2 is mass of the solute. R is solution constant having the same value of 8.314 joules per Kelvin per mole. T is absolute temperature or Kelvin temperature. Pi is osmotic pressure with respect to the what solution? Dilute solution. And V, no subscript, means it is called as a volume with respect to the solution. Okay. So this is about the fourth colligative property, that is the last colligative property with respect to the solution, that is called as what pressure? Osmotic pressure. Okay. Now, next is what is abnormal colligative property and abnormal molecular mass, and what is Van 't Hoff factor. Let's have first abnormal colligative property. After that we are having the abnormal molecular mass. Okay. So then what is that abnormal colligative property here? It is a property or physical property of a dilute solution. Which solution here again? The dilute solution. What in general the colligative property we have defined as? It is strictly the physical property with respect to the dilute solution depending upon the number of moles of solute particles but not upon its chemical nature or it may be the size. But what is abnormal here? It is also the physical property of a dilute solution. It's a physical property with respect to the dilute solution. Dilute solution where observed when it gets either when the solute in it gets either dissociated or associated. Means it is a property only obtained that has been after either the dissociation of solute or it may be the association of the electrolyte. So then we are having the abnormal molecular mass. Abnormal what mass? Molecular mass. What is abnormal molecular mass? It is the higher or the lower value of molecular mass of a solute obtained as that from the observed, or it is also called as experimental value. Means either get the higher value of that molecular mass or the lower value. So that is due to the what property? Abnormal colligative property. Abnormal colligative property means it is found to be the different or it is found to be the as that obtained with respect to the observed or it is maybe the experimental value. Means why this difference is means that substance has to undergo a term called as which one? Either dissociation or it may be the association. So okay. So that we need one term that is called as Van 't Hoff's factor. Van 't Hoff's factor. So here Van 't Hoff factor I is given by Van 't Hoff factor definition is it is a ratio of observed or it is also called as experimental Cp. Cp means it is colligative property divided by theoretical or it is also calculated colligative property. Means it is the ratio of what by what? Observed or experimental colligative property divided by the theoretical or it may be the calculated colligative property. So this can also be written as in terms of molecular mass or first we will mention this and then we will have the number of particles present after dissociation or association divided by initial number of moles particles present before either dissociation or it may be the association. It is a ratio of what by what? Either the number of particles that has been present either after dissociation or it may be sometimes dissociation divided by the initial number of particles or the moles that has been present before association or it may be the association. Or it can also be mentioned in the form of I is equal to the theoretical or it is also called as calculated MM means it is called as molecular mass divided by observed or it is also called as experimental MM. Here it is observed divided by theoretical with respect to colligative property, but here it is theoretical divided by observed with respect to molecular mass, because this shows that Cp is inversely proportional to mm. Colligative properties, they are always inversely proportional to its which mass? Molecular mass. Okay, so that Van 't Hoff factor is given by either the ratio of what by what? Observed, or it is also called as experimental colligative property divided by the theoretical or calculated colligative property, or in terms of association or dissociation, it is a ratio of number of particles or the number of solute particles that has been obtained after dissociation or association. There are two possibilities here, divided by initial number of particles that has been present before either dissociation or it may be the association. Or in terms of molecular mass, it is given as I is equal to what? Theoretical or calculated molecular mass divided by observed, or it is also called as experimental which mass? Molecular mass. Based on that, we have proved that, or we have taken that as colligative property is inversely proportional to its which mass? Molecular mass. Now, what is its value? What is its value? See here, value of Van 't Hoff factor I for, what's the value of Van 't Hoff factor I? First one, for non-electrolyte, what's the meaning of non-electrolyte? Means which further get dissociated or it may be sometimes associated. If this be the case, I is equal to 1. Means before and after, because as if the non-electrolyte itself doesn't undergo either the dissociation or it may be the association, means the I factor is always equal to 1. Means the observed colligative property is exactly equal to the theoretical, or the theoretical molecular mass is exactly equal to the observed molecular mass. That ratio is always equal to 1 if it is an example for a electrolyte. Then the second case is for electrolyte. Electrolyte are the chemical substances which conduct electricity either in the fused state or maybe in the aqueous state, but not in the solid state. Here, I not equal to 1, because either it can have the dissociation or it may be the association. Means I factor is not equal to 1, means the observed colligative property is not equal to that of the theoretical with respect to colligative property. So under that, we are having the two options. For electrolyte undergoing dissociation, if it undergo what? Dissociation, I factor is greater than 1. I factor is greater than 1. Which undergoing, or electrolyte which undergoing association, means I factor is less than 1. I factor is less than 1. For example, NaCl I is equal to 2. Barium bromide I is equal to 3. How we are getting this? Because NaCl is an electrolyte which gets ionized to form what and what? Na plus and Cl minus. What Na plus and Cl minus are? They are the individual particles of a solute called as NaCl. Therefore, how many Na plus and how many Cl minus? 1 Na plus and 1 2L minus. Therefore, the Van 't Hoff factor is found to be the what? 2. Barium bromide, barium 2 plus and bromide minus, means 1 barium ion and 2 bromide ions, means totally how many ions are there? 3 ions are there. Therefore, the Van 't Hoff factor is found to be the what? 3. The Van 't Hoff factor is found to be the what? 3. Acetic acid in benzene, instead of this it undergo dimerization. If it undergo dimerization, means I is found to be 0.5. Why? Because two molecules gets associated. Two molecules gets associated to form a single particle due to the hydrogen bonding. So that is why the process is called as dimerization. What is the meaning of dimerization? Combining of two particles and making as one, means we have taken that as 2, but the number of particles that has been obtained after dimerization or association is only 1. Therefore, what is its Van 't Hoff factor? It is found to be the half. If I take 1 mole of NaCl, means I am getting 2 particles. Why? 1 mole of Na plus and 1 mole of which one? Cl minus. This is called as dissociation. But in case of association, I value is always less than 1. Okay. Now, what is degree of dissociation and what is degree of association? Expression for degree of dissociation. Expression for which one? Degree of dissociation. Alpha is equal to I minus 1 divided by n minus 1. What's alpha here? Alpha is DOD, degree of dissociation. I is called as Van der factor. What is n? Number of particles present after dissociation. After dissociation. For example, NaCl, n is equal to 2. Then we are having aluminium sulfate, n is equal to 5, because Na plus and Cl minus. How many particles that we have mentioned here? 2. Aluminium sulfate means sulfate is minus 2 and aluminium is plus 3. Here 2 aluminium and 3 sulfate, totally what? 5. And that is n here. And then what is alpha here? The degree of dissociation. What is degree of dissociation? It's a part or fraction of 1 mole of an electrolyte that has been undergoing a dissociation. Okay. Similarly, we will have the last one in the form of expression for degree of association. Degree of which one? Association. Alpha is equal to 1 minus I divided by 1 minus 1 by n. In case of degree of dissociation, alpha is equal to I minus 1 divided by n minus 1. I factor is always greater than 1 for dissociation. Therefore, it is I minus 1. For association, I value is less than 1. Therefore, it is not I minus 1, it is 1 minus I divided by 1 minus 1 divided by n. So, here what is alpha? Degree of A. A means it is called as association. What is n? Number of particles associated. Number of particles that has been associated. So that is the difference here. Here n refers to the, in the first case, number of particles that has been obtained after the dissociation. Dissociation means it is splitting. What is the same case n here? In case of this one, it is the number of particles that has been associated. As if I mentioned, dimerization means n is equal to 2. Why? Because we have taken how many particles? 2. But we have made that as what? 1. Okay, so that is n is the number of particles that has been associated. So this is called as a degree of dissociation and degree of association. These two comes if and only if the substance is an example for an electrolyte where its value is always not equal to 1. If it undergo an electrolytic dissociation, I greater than 1. If it is say electrolytic association, I less than 1. Suppose strictly if it is a non-electrolyte, means I factor is always equal to 1, because non-electrolyte means it neither gets dissociated nor gets associated. Okay, so this is about the which factor? The Van der factors. Okay, then lastly we will have the expressions for various colligative properties using Van der factor I. What are various expressions with respect to the colligative properties using the Van der factor here? The first one is pi is equal to I into CRT. I into CRT. Pi is equal to I into CRT. Or pi is also equal to I into W2 RT divided by M2 into V. So previously I mentioned one expression, that is molecular mass. How molecular mass is calculated? M2 is equal to what? W2 RT divided by pi into V. But to get a what pressure? Osmotic pressure. An example for a what property? Colligative property. Suppose if it is an electrolyte, means we have to add this term in the form of which one? I. What I is called as Venter factor. If it is non-electrolyte, no doubt it is simple, only I is equal to 1. Suppose if it is an electrolyte, we have to choose the two options. Whether that electrolyte is undergoing a dissociation or it may be the association. If it is dissociation, means I value is always greater than 1. If it is undergoing association, means its value is less than 1. Okay. So let us have the second one. This is the concept of which one? Osmotic pressure. Okay. Pi is equal to nRT. Then we are having the lowering of vapor pressure. Let's have the first one. Lowering of vapor pressure. Lowering of vapor pressure is M2 is equal to P0 minus P is equal to I into P0 W2 M1 divided by M2 into W1. Lowering of what pressure? Vapor pressure. That is P0 minus P. Actually, we have mentioned M2 is equal to P0 divided by P0 minus P. Or P0 minus P is equal to an additive factor. What is that? I. I into P0 into W2 M1 divided by M2 into S1. Okay. So that is with respect to lowering of what pressure? Vapor pressure. Then with respect to the elevation in boiling point. Elevation of what point? Boiling point. Delta TB is equal to I into 1000 times the value of Kb W2 divided by M2 into W1. Previously what I mentioned? M2 is equal to 1000 Kb W2 divided by delta TB into W1. But to get the elevation of boiling point, delta TB is equal to what? 1000 Kb W2 divided by M2 into W1. But if it is an electrolyte, means we have to put the which property, which factor? Van 't Hoff factor. So this is one concept here. There is another formula related to that. Delta TB is equal to I into Kb into M. What is M there? Molality of the solution. What is that? Molality of the solution. If this we get, means again the same thing for depression of freezing point. Delta TF is equal to I into 1000 kf W2 divided by M2 into W1. Instead of Kb, have mentioned Kf. Delta TB, here it is delta TF. Or here delta TF is equal to I into Kf into M. What is Kf here? Cryoscopic constant. M is the molality of the solutions. What these are? The expressions with respect to the colligative properties. If it is an example for an electrolyte, electrolyte means it contains a what factor? Van 't Hoff factor. Okay, just you have to multiply. Towards the left we are having all the what properties? Colligative properties called as osmotic pressure, lowering of vapor pressure, elevation of boiling point and depression of what point? Freezing point. Towards that we are having the rest of the same symbols, but along with we are having an addition in the form of what? I, Y. What's that I is called as? A Van 't Hoff factor, which is for non-electrolyte, no doubt I value is always equal to what? 1. But suppose if it is an electrolyte, means there are two possibilities. If the electrolyte undergo dissociation, means I factor is greater than 1. If it is an electrolyte undergoing a association, means I factor is less than 1. Okay. So this completes, I think, the overall theoretical portion related to the which one? The solution chapters. Okay. In the next session, we will have the solving of the numerical problems relative to the solution chapters. That is, we are having the three different concepts. One is solid liquid solutions, which is for a colligative properties, liquid solutions, which is indirectly the application of Raoult's law of liquid mixtures, and finally the gas liquid solutions, which is the application based on the what law here? Henry's law. All these three different tasks, that is in the form of liquid solutions, we are having the numerical based. So with respect to colligative properties, we are having the 4 formulas. With respect to Raoult's law of liquid mixtures, we are having only 1, and with respect to the Henry's law, it is also found to be the 1. In addition to this, you have to be very familiar to calculate the concentrations of the solutions with the help of 9 concentration terms that I have mentioned. Usually that we have already majorly discussed that in the first year PUC or in the class 11th. That is molarity, molality, normality, formality, mole fraction, parts per million, mass percentage, volume percentage, and then the mass volume percentages. Okay. So, but apart from that, we are having to concentrate on the calculation of molecular mass with the help of the 4 different colligative properties called as osmotic pressure, lowering of vapor pressure, elevation of boiling point, and then the depression of which point? Freezing point. Apart from that, for liquid solutions, we are having the Raoult's law of liquid mixtures, and for the gaseous solutions or gas liquid solutions, we are having the what law expression? Henry's law expression. Okay, so that all we will solve in the numerical sections, that is the numerical problems related to the solution chapter. Okay, so thank you very much.